All right, so we're going to work through investigation 1.4. So turn in your red folder to page 11. So page 11 in your red folder. Okay, so the start of this is just a little bit of review. I first want you to think about what these walkathons might mean, okay? We're going to have M stand for money and K for kilometers. All right, so if the walkathon plan says money is equal to 6 times the kilometers, what do you think that might mean? Okay, so do you think that plan was to ask for $6 per kilometer walked? All right, how about if the equation just M equals 30? So money is just going to be 30. Okay, did you think that that was just going to be like a $30 like flat donation? Okay, kind of like Michael Scott was thinking. All right, how about this one? It's a combination. It says M equals 1.5K plus 10D, plus 10, sorry. What do you think that means? Did you think that since the rate was $1.50, that it meant $1.50 per kilometer walked? Okay, and an additional $10 donation? Okay, so now we're going to see if we can pull out those ideas from a table of values. So this first one is kilometers. So 0 kilometers, money would be 0. 1 kilometer, money would be $2. 2 kilometers, 4, etc. So what do you think this one might mean? So did you think it represented $2 per kilometer walked? Okay, so because if we walked 5, it would be 10. Okay, no upfront amount because it started at 0, 0. Okay, what do you think this means? So 0 kilometers, $5, 1 kilometer, $5, 2 kilometers, $5. Did you think it was a $5 flat donation? Okay, so just like Leanne, it didn't matter how many kilometers walked, the money was still just going to be $5 the whole time. Okay, how about this one? So 0 kilometer, $10, 1 kilometer, $10.50, 2 kilometers, 11. What do you think this one might read? So did you think 50 cents per kilometer and $10 donation? Okay, so you got $10 no matter what, and then an additional 50 cents each kilometer walked. Okay, let's look at these graphs. Okay, and I guess a little bit of, so on the bottom would be the number of kilometers. And we're just going to assume the scale is 1, and over here is going to be the dollars, so the amount of money. Okay. So let's look at line A. So 0 kilometers, $0, 1 kilometer, $2, 2 kilometers, $4, 3 kilometers, $6, etc. You think money is equal to $2 per kilometer? So just, I guess we don't need the dollar sign. So 2K. Let's look at B. Okay, so 0 kilometers, 1, 2, 3, 4, 5, 6, 7, 8, $9. 1 kilometer, $9. 2 kilometers, $9. Do you think that just money is equal to 9? Okay, how about C? 0 kilometers, $5, 1 kilometer. It's a little hard to tell. Looks like you have to go out 4 kilometers to make another dollar. So how much do you think that might be per kilometer then? I think M is equal to 25 cents per kilometer, plus a $5 donation. Okay, so we're saying that the number that's multiplied by kilometers is the amount you get per kilometer. Okay, so the unit rate, and then any number added on, okay, is the amount of a donation. Okay, so let's look at 8. Okay, so, oh, and I guess I did go to kind of equations there. I probably should have just said that what that one meant, $2 per kilometer. Okay, and then this one was $9 donation. Okay, this one, 25 cents per kilometer. A $5 donation. Okay, make a table for a $5 donation plus $2 per kilometer. Okay, so kilometer is 0. You're still going to get $6. Kilometer is 1. You're going to get $6 plus the $2 for that kilometer, so that'd be 8. Okay, if we walk 2 kilometers, so 2 times 2 plus the extra 6. So it's going to go up to 10. Okay, do you see how it's starting at 6, increasing by 2? Okay, how about an equation for a $3 per kilometer plus a $5 donation? Okay, our money is going to equal 3 times the amount of kilometers plus $5 added on. Okay, what will the graph of a $4 just donation be? Let's just add it to the graph. So nothing, it's just a flat donation. I'm just going to go 1, 2, 3, 4 and just go straight across. See what that one looks like. Okay, so hopefully that was a good review of what we did in the first couple sections. Okay, so let's look at page 14 in our textbook. Okay, so it says using walkathon money, recognizing linear relationships. In previous problems, you notice that as the independent variable changes by a constant amount, there's a pattern of change in the dependent variable. You can use this pattern of change to identify other linear relationships. Mrs. Cheng's class decides to use their money from the walkathon to provide books for the children's ward at the hospital. The class puts the money in a school safe and withdraws a fixed amount each week to buy new books. To keep track of the money, Isabella makes a table of the amount of money in the account at the end of each week. Okay, so here's at week 0, we've got $144. After 1 week, we now have $132. After 2 weeks, $120. After 3 weeks, $108. 4 weeks, $96. 5, $98. So let's take a look at that. Okay, let's see if we can answer the first question. So A says, how much money is in the account at the start of the project? Okay, so let's see, how much money is at the start of the project? Did you say $144? Because if we look at 0, that's how much we're starting with. Okay, so second question, how much money is being withdrawn from the account each week? Okay, withdrawn, so taken out. Okay, so we got 144, and then it goes to 132, then to 120, then 108. Okay, so did you say $12? What it's decreasing by. Okay, so number 3 says, suppose the students continue withdrawing the same amount of money each week. Sketch a graph of this relationship. So just a sketch. What would this look like? Okay, so this is weeks and this is money. We kind of started up here at 0 weeks with 144. Okay, and then as the weeks progress, what's happening to this? Okay, so did you think that it would end up looking like this? Okay, so a line going down, it should be a straight line because each week we're dropping $12. So eventually after 12 weeks, the money would pretty much be gone. Okay, question 4 says, write an equation that represents the relationship. Explain what information each number and variable represents. Okay, so how much money based on the weeks? Okay, so did you think that I'm starting with $144 and each week I'm subtracting $12? So I'd have to multiply 12 by the number of weeks. So like after 1 week, I'd only take away one $12, but after 2 weeks, I'd have taken away $24. So 2 times the 12 after 3 weeks, so 3 times the 12. So I'd take away 36, etc. Okay, so question number 5 says, is the relationship between the number of weeks and the amount of money left in the account linear? Okay, well, what does it take to be linear? Well, 1, remember, it comes from a line. Didn't we think the graph would look like a line? Okay, and secondly, can't we tell from the table that it's linear? Because each week is just going down by the same amount, by 12. Okay, so we should say yes. Graph is a line. Line. And the table decreases by the same amount. By the same amount. Okay, let's look at question B. Okay, here's a graph on the next page. It says Mr. Mamer's class also raised money from the walkathon. They used the money to buy games and puzzles for the children's ward. Keenan uses a graph to keep track of the amount of money in the account at the end of each week. So at the beginning of the week, it looks like they've got $100. After 1 week, they have 90. So what do you think this means? What's going on with the money in Mr. Mamer's class account? Okay, so did you say they start with $100? And spend $10 per week? Okay, so then question 2 says make a table. So in week 0, how much did they start with? $100. Okay, and then week 1, they've spent $10, so now they've got 90. In week 2, 80. Okay, 70, 60, 50. Just keep decreasing by 10. Okay, and eventually after 10 weeks, they would have no money left. Okay, so write an equation that models this. Okay, so it's weeks and months, or money. So the money, they're going to start with $100, but instead of adding them out, they're subtracting $10 per week. Okay, so $100 subtracting $10. So after 4 weeks, we'd subtract 40, so 4 times 10 from that amount. Okay, and then the last question is C number 1. It says, how can you determine whether the relationship is linear from a graph, a table, or an equation? Okay, so from a graph, looks like a line. From a table, as x, the first variable, okay, as the x goes up by 1, y goes up by the same amount. Okay, and then how about from an equation? Okay, so from an equation, it looks like y equals something times x plus something. Okay, so some multiplier times our variable plus some other number. Okay, all right, so that's the end of 1.4.